All right, welcome back, Algebra Express students. Hopefully your first week went well. And so today we're going to do Merecek chapter 2.3 that's titled Solve a Formula for a Specific Value. And so during the first couple things, we're going to do a few formulas. We're just going to rearrange letters to solve for a certain letter. And then they're going to give us a few geometry formulas that we'll go through. And that should complete the lesson then after that. So we're going to start off with this thing. This says solve for W. So if we want to solve for W, we're going to solve for the single letter W. So we're not working with anything with higher exponents. So everything is an exponent power 1. So if it had a higher exponent, we would have to get this down to 1. So we don't really have to worry about exponents here. But when we solve it, we have to get it down to single power 1 in front, 1 in the exponent. And so we're looking at W. So W is being multiplied by 2 here. Further out, it's being added to 2L. And so when we're solving this, it's sort of like we're back solving for the variable. And so the furthest thing is actually the first thing that we want to do. So if we see plus 2L out here, this is further than the multiplying by 2. So we want to get rid of this 2L. So we want to move this 2L over. And so this is the operation of addition. So in order to get rid of something that is being added, we have to subtract. And if we subtract 2L, we subtract it from the right side. We also have to subtract it from the left side. So on the left side, I have something like P minus 2L. And this is equal to 2W. And so we still want to solve for W. And this thing still has a 2 attached to it. This 2 is the operation of multiplication. So if we want to get rid of something that's multiplying, we have to divide. So we have to divide each side by 2. So this entire side has to get divided by 2, and this entire side has to get divided by 2. And then we have P minus 2L over 2 is equal to W. And we've solved for W. So if you have this is good. There's one other thing that students might do, and that's to divide each of these by 2. So if we go P over 2, and so just as like we did when we added fractions, we found a common denominator. We put them over that common denominator. Now we're going kind of backwards to separate things. So now we have a common denominator. We want to put each of these things over a common denominator of 2. And so this looks like P over 2. This looks like 2L over 2. And this is my W variable. And so one thing you might do to clean this up is you might recognize this is a 2 over 2. And so this simplifies to 1. And so this looks like P over 2 minus L equals W. And if I'm being honest, I don't think that's any much cleaner than that, if at all. And so either if you got that for your solution or you got that for your solution, either way should be correct. Okay. And this is one of the formulas we'll talk a little bit more about later. This is what? Perimeter of a square, I believe is what that is. And so for part 2, problem 2, if we want to solve this thing, 3x minus 2y equals 4, and we want to solve this thing for y. So same thing. The first thing I see that's attached to this y, it's being multiplied by 2. And then we have this operation of addition, subtraction, and further out there's a 3x. And so if we're adding and subtracting, we want to move the 3x over. We want to get this y by itself. So in order to move the 3x over, the operation's addition, subtraction. This is a positive 3x, so we want to subtract 3x. And if I subtract 3x, the left side is minus 2y. This is equal to, I'm going to lead with this term. So I'm going to put the minus 3x first. And so instead of doing 4 minus 3x, I think I'm going to do minus 3x. And the operation is addition and subtraction. And I'm going to put plus 4. So we still want to solve for y. Y is being multiplied by a negative 2. If this operation is multiplication, then the thing that I really want to do is division. So I want to divide this side by a negative 2. I also want to divide this side by a negative 2. So if we're looking at this, on this side we have negative 2 over negative 2. So this is going to become positive, and it's going to become a positive 1. And so the left side is y. The right side, I want to do a little bit of cleaning over this thing. I want to do the same thing I did in the previous problem. So we have a common denominator. We can put each of these things over a common denominator. So I see a negative 3 over a negative 2. I'm going to go ahead. I see 2 negatives. This should be a positive overall. So I'm going to drop the negative because there's 2 of them. And I'm going to put that as a 3/2 x. And I see this next thing, 4 over minus 2. So this one is going to give me a negative. 4 over 2 is going to give me minus 4 over 2. So I can do a little bit of cleaning. And you might notice I threw the x out in front. Y equals. So whether the x is out in front or whether it's in the numerator, that is technically the same thing. And minus 4 over 2. If we divide 4 by 2, we're getting 2. And so maybe when I was back here doing this, you might not have really understood why I put this x term first. But if we're looking here, this looks like, hopefully it looks a little bit like y equals mx plus b, right? With this is a linear equation. And I put it in this order sort of because it has context to being a linear equation, right? Just kind of doing things by convention is what I'm doing. Okay. Same thing, we're going to solve for y on this last one. So if this is my y, it's being multiplied by negative 3. Further out, I see this addition subtraction sign. I see a minus 2x. And so if I'm adding and subtracting and it's a minus 2x, the first thing I want to do is add 2x to both sides. So on the left side now I have a minus 3y. On the right side, I start with a positive 2x, and I still have a minus 5 there. So now I look at this thing. I have a minus 3 times a y, and I have 2x minus 5 this side. So I want to get the y by itself. This is multiplication. So it's the same step we've been doing. We want to divide by minus 3. So I'm dividing by minus 3 both sides. This is the same thing over itself. This is my big fancy positive 1 here. So the left side is now y. The right side, I have 2x over minus 3. So overall, this should be negative. I have 2 over 3. And this is the thing with the x on it. I can put it in the numerator. I can put it out in front. And I have a minus 5 and a minus 3. So this has 2 negatives. This should be plus now 5/3. So on this page, they start with a few geometric problems. And so the definitions they give is that supplementary is 180, that complementary has a sum of 90, and that triangle sum is 180. So what they really mean is that the interior angles of the triangle sum to 180. So what they're talking about is these 3 angles, when we measure them up, they're going to add to 180. What they mean for complementary is that when you add these 2 angles up, they're going to add up to 90. And supplementary, when we add these 2 angles up, they'll add up to 180. Didn't quite make that one. There you go. Okay. So something a little silly. But one way, and I remember Miss Thomas when I was like in what, 5th grade, I think she told me this. C was 90. If a C or complementary is 90 degrees, and it's a bit silly, but it takes 2 C's to make an S. And so it takes 2 90 degrees to make 180. So if you have trouble remembering the vocabulary, complementary is 90, supplementary is 180. It takes 2 C's to make an S. And that's how I learned it when I was in, what, 5th grade, I believe. Okay. So let's read the problem. If one angle measures 10 degrees more than its complement, find both angles. Okay. So if we read this, if one angle measures 10 degrees more than its complement, find both angles. So how many angles do we want to find is the first question that I hope you answer. And so if you're thinking about this, it's complementary. There's an angle and there's its complement. They're talking about 2 angles here. And so we want to know what both angles are. So our first variable is just one of the angles. So x is the first angle. We know that one angle measures 10 more than its complement. And so if this is the first angle, the other angle measures 10 more than this one. And we want 10 more than this one. So 10 more than this one would be x plus 10. And so this would be the other angle. So we have the first angle, we have the other angle. The other thing we know, they are complementary, which means they sum to 90 degrees. And so we want to create we've defined our variables. Now we want to create an equation that represents what they're telling us. And so I want you to think for a second how to do this. And so the equation, I want to know how many of you put that. If you put that, you're only solving for one angle. So this is the other angle. you're not going to get two complementary angles if you do that. So what you're missing here is the first angle. So we still have to add the first angle. So this is the first angle. So we have to add the first angle, and we have to add the second angle to get to the 90. So a lot of times people will look at this equation, x plus 10, and then think that for some reason that this should add to 90. This is only one of the angles. We have to add both of the angles. So you have to come back. You have to add the first angle to your second angle. So the first angle, add it to the second angle, and this should be the thing that gives you 90. Okay. So if we set up the equation like this, this should not look a whole lot different from the things that we've been doing throughout class. And so we're looking at this. We look at the left side. Let's clean up the left side a little bit. I have a 1x and a 1x. If we add those, it's going to give me 2x. And I'm going to have plus 10, and this is going to equal 90. So I am solving a first order single variable equation. So 2x plus 10 equals 90. I want to subtract the 10 from both sides next. So 2x equals 80. I want to divide by 2. So x is going to give me 40. At this point, you're probably like tempted to box this thing. Okay. What were we doing? So let's take a step back for a second. What are we doing here? What did it ask? It asked for an angle and another angle. And so we found this, and this is talking about degrees. We're talking about an angle. That is, and on this page. So x would be the first angle. So we still need to find the other angle, which looks like x plus 10. So the x is 40. So that is my first angle. So I still need to find x plus 10, which is my second angle, or 40 plus 10, which gives me 50 degrees for the other angle. Okay. So that was finding two complementary angles. So I think if I asked a little bit about geometry and where geometry came from, I think most people have a pretty good understanding that geometry has origins in ancient Greece, right? And so just to elaborate a little bit on that, the guy that came up with a lot of things, his name was Euclid, and he wrote this piece called The Elements. And we're talking about around 300 BC is when he first did this. And this ties back to that sort of thing I was talking about in a previous lecture, where math is just an application of deductive logic, right? And so what happens is we use deduction to prove new things and to come up with new truths. But the thing with true statements or I want to say conjectures is that at some point you have to start somewhere. And what I mean by that is I think it's like the 2-year-old blues. If you know someone that's had kids, or if you have had kids yourself, there's an age that kids reach, and it's like usually right around like 2 years old, and it's just the why phase, right? And then it's like you go outside and the grass is green, and the kid asks, why is the grass green? And you're like, well, it's got chlorophyll, and then the chlorophyll takes the sunlight's energy, and it converts it into energy for the plant. And you go in this whole explanation of things, and the kid still goes, why, right? And then you try to explain it more, and the kid is still just like, well, why? You know, and they just keep asking you why, and they keep asking you why, and they keep asking you why, and you try to boil it down more and more and more and more, and at some point, like you just like the frustration gets to you, you start like invoking almighty deities. You're just like, I don't know, it's the way God made it, right? You just like you just don't know, and so at some point you just have to start somewhere and just like you have to kind of accept things for being self-evident, right? That's the word that they use. It's not something that maybe you should set well in your gut, right? If someone tells you something self-evident, you should definitely like probably try to question them a little bit. But to keep from going insane, we have to start somewhere, right? And these things that we start at are these basic sort of rules called axioms. And that's exactly what Euclid was doing with geometry. He was creating these self-evident rules called axioms. But it turns out there's actually, and it's called Euclid's fifth postulate if you want to look it up. There's this rule he wasn't really too sure about, and it turns out depending how you interpret it, you can actually come up with other forms of geometry. So I believe there's hyperbolic is the other form. And the other thing I'm talking about is elliptic geometry. So there are actually other areas of geometry, and we did throughout this rule. This rule, where triangles sum to 180, is only true in Euclidean geometry. So the Euclidean geometry, or is what regular geometry that everyone gets taught is called. So I can almost guarantee you've never even seen like these two other geometries at this point in your math career. Like these, they won't even start talking about these things till later. But everything that you've ever learned, every geometry is Euclidean geometry, or not every geometry. Every geometry that you've learned is Euclidean geometry. And that comes back, you know, he's the guy that wrote the book. And this thing was around for, I don't even know, amazing amount of years. I think they still have it around, to be honest. It got translated and retranslated. It was really sort of a prestigious thing to be able to translate this into Latin for the longest time. And people would just read this in Latin. And so that's Euclid. If you want to know a little bit maybe about like number sets, and these are not the funnest things to write, they're self-evident rules about math, right? They're really basic sort of rules. Another guy, Piano, was the guy that wrote a lot of axioms about like the natural numbers that we're going to talk about. And so that might also be a good resource to sort of think about these things. And just to kind of put everything into perspective, we have these axioms that we start off with. And from these axioms, we want to deduce new things, right? We want to come up with new rules. We want to start out with some sort of like basic rules. We put the two basic rules together. We come up with new things in math called theorems. And this is how theorems in math are derived. We use deductive logic on quote unquote, you know, self-evident rules. And then we deduce these things called theorems, which are also true, right? And these things called theorems, they're true mathematically and in a deductive sense, right? And so there is a really sort of strong truth happening to math theorems that we may not necessarily get in the real world, right? Or in reality out there. And so in my early career in math, I really appreciated math for its certainty. It wasn't sort of wishy-washy like some English professors can be sometimes, right? It's like, well, what does this mean? It could mean this or it could mean that. It's like, I'm not sure about that. But where is that? That. And so that's basically all of math right there. We're putting together axioms, or we're putting together two theorems to create a new theorem, right? We can do an axiom and a theorem to create a new theorem, but we're developing theorems from axioms and from previous theorems. Okay, and so now I want to talk about area, perimeter, and circumference. Okay. And so for rectangle, I think this one, the first one that they give you, might be the most straightforward. If I have something, area is length times width. So if I have something that is, I don't want to draw this again, I have it in my notes. So if I have something that is 4 inches by 6 inches, and I've marked my little inches off, if you think about the area in here, I'm going to have 24 square inches in here. And you do that by multiplying the length and the width. And so this is sort of like, it gets at the definition of what the heck is area, right? And so I'm using the unit inches here, so that might be the note. But what does area mean? What if I say this is what, 24? The next word I'm probably going to use is square inches, right? This is a area measurement. I'll get it right eventually. So we're talking about 24 square inches, but what does that mean? Well, when we work in one dimension, we have a single dimension of an inch. When we work in 2 dimensions, what we have isn't a single dimension. We have little blocks. And these little blocks are 1 inch by 1 inch. And what this means is that if we have something that's 4 inches by 6 inches by 4 inches, we can actually fit 24 of these little blocks in here. So I know like this is not the straightest drawn picture, but pretend like all these things are even and these are 1 by 1 inch blocks, right? So I know I drew this by hand and it's not even. It should technically be. Let's pretend. You all have healthy imaginations. And so that basically gets at the concept of area. The other thing there is perimeter. And so if I want to go around this thing, I have a rectangle, I have a length, I have a width, I have a length, I have a width. Woo, there we go. The perimeter, and hopefully, yes, is a single dimension, and it's like you're walking around the outside of an object. So if we walk around the outside of the object, right here I'm going to do a length, I'm going to go here, I'm going to do a width, and then I'm going to do another length, and then I'm going to go do another width. And so I'd want a length, I want a width, I want a length, and I want a width. And so this goes back to the commutative property. It doesn't matter what order I can write these things. So I have 2 L's here, and I have 2 W's that I can put together. So this is how I'm getting my perimeters: 2L plus 2W. Okay. And so the next thing, that is rectangles. Area is length times width, and the perimeter is 2L plus 2W. The next thing we're going to talk about a little bit about is triangles. So for triangles, they give you 1/2 base height. I want to ask you if you know where that's coming from, I guess. And so one way you can think of this is that we know a rectangle is length times width. So if you take a rectangle, and if you want to half a rectangle, I think that's probably the best way to start this. If we want to half this rectangle, what's the easiest way you could probably think about halving this rectangle? And maybe I should put my length and my width on. What I would think is you split it right down the middle, right down its diagonal. And if we do that, you might notice that we have a half. Or that the area of the rectangle would be the width times the length. If we want half of that, it would be half its width and length. And so if this is a right triangle, the width and length is the same thing as saying base and height. So for right triangles, the two sides are the base and height. Now that's for right triangles. If we don't have right triangles, and this is we're talking about area, my area formula on here. If we don't have a right triangle, so let's draw a triangle that's not right. Not right. Okay. So this is not a right angle. So if we want a height, the way we get a height on a triangle is we draw a diagonal that comes down at a right angle. And so if it's not a right triangle, we create a right triangle. We create right triangles out of it, basically. And so now we have this thing. This is going to be our base here. This thing all along here. This side of the triangle is our base. This thing right in here, the thing I just drew, is my height. So the height always comes 90 degrees perpendicular to the base. And it always intersects the opposing angle. Okay. So if we don't have this, and I'm going to write, I can kind of sort of divide this into maybe like, I'm going to do this as my base part 1. Maybe this is my base part 2. And I want to look at these separately. So if I look at this left triangle over here, if I want to know the area of that left triangle, it is going to be 1/2 my base line. I want to know the total area of this thing. Now I'm just looking at the right half. I want to know just the area of this right half. That's 1/2 my second base times my height. And if I want to know the area of the total thing, I add these two together. There's a little trick I can do. Both of these have 1/2 height. If I pull that, I'm just adding my two bases together. And if I do my two bases and I add my two bases together, this is the same thing as all of my base, right? Base 1 and base 2, when I add them together, are going to create the whole base. And so this is just a half base height. And so essentially what we have is we have a right triangle is essentially like cutting a rectangle in half. And if we don't have a right triangle, we're creating right triangles. And when we add the area of these things together, the right triangles, they're going to be the same half base height. And so that's a little bit behind where the area of a triangle is coming from. Okay. The next thing I believe is area of a circle. So we'll talk about area of a circle in just a second. Circumference of a circle, I think, is probably the easier one to start talking about. And circumference of a circle, this says 2 pi r. Circumference is 2 pi r. But we know 2 times the radius is the diameter. So another way I can write 2 pi r is I can think about 2r as just my diameter and pi. And this is actually, I think, one of the ways in which they can actually define pi, is it is the ratio. If we move the ratio of my circumference to my diameter. So my pi is telling me how many diameters I can fit in my circumference. And another way to look at that, maybe, let's look. If I share my screen, let's see if I can look at this. There's a GIF that might be of use. So this, we're rolling it out. We're rolling out a circle. Each diameter is 1, right? So each diameter is 1. And if we roll out the circumference, we can fit 3 and a little fraction of our diameters in there. And so hopefully this GIF will help you a little bit. But now we need to talk about the last one there. Area of a circle, pi r squared. Ooh, excuse me. So, where's this pi r squared coming from? Okay. So there was something that the Greeks did. It was a little odd. And I believe Eudoxus was one of the first people to do this, and then Archimedes also picked this up a little bit. But they would inscribe circles. They would inscribe shapes inside circles. And I believe they did it by inscribing and circumscribing. So I believe Archimedes actually would put like a rectangle on the outside as well. He would put a pentagon on the outside. There'd be a bigger one and smaller one, and he would kind of sandwich the circle between the two shapes. I think is the way that Archimedes did it. But there's a observation that they made that I want to sort of make here. And we start out with the four-sided figure. We can do this sort of thing. And we can look at these as triangles. And so the more sides you get, the more triangles you're going to have. But they also notice something else. The more sides you get, the more it's starting to look like that circle. And so we can fill these circles with these shapes. And part of the reason why I think Eudoxus didn't get this is that we're making an argument sort of like about infinity, right? We can fit infinitely many sort of triangles into the circle. Ooh, poorly, John. Do it real quick. And so if we get infinitely many triangles in the circle, then we can get at the area of this circle. And so let's think about how to do this maybe. So if we cut, let's assume there are infinitely many triangles here. If we cut this sort of thing, we cut it like along here, and let's just kind of like lay out these triangles. So we're pretending like we're cutting this thing open and we're rolling this thing out. And so we're rolling these triangles out all along here. And so if we look, I want to know what the height of this thing is. And so if I'm looking at my height, the height of these triangles is the same as the radius of your circle. So I have my height. I want to look along here at what my base is. Well, each one of these triangles has a separate base. But when we add all these bases together, they should be the circumference of our circle. And so we have this thing, and it's like a bunch of triangles. And these are our bases. This is our height. And sort of the same thing, if you wanted to do base 1, base 2, base 3, right? Like we were doing in our previous problem, you can do that. But it's still going to factor out like it did in our previous problem. So really, we don't need to separate these bases. All we need to do is 1/2 base height. And if we do 1/2 base height, we're filling this in. This is 1/2 of a circumference times a radius. We know the circumference is 2 pi r. Sorry. 2 pi r, and we still got to multiply that by r. And I'm getting closer, but 1/2 times 2, that's going to simplify to 1. And now this just gives me the pi r squared. And so if you know how to find the area of a triangle, and you know how to throw triangles into a circle, you can actually find the area of a circle. Okay. And I think I know I went over it. But I'm not sure if I stated it explicitly. We had this thing over here called perimeter. So perimeter is like when you walk around the outside of a rectangle. We can find perimeter with triangle. Over here, we use this word circumference, but really circumference is just a big fancy way to say the perimeter around a circle, right? It is not really any different than saying perimeter. And so hopefully, I hope you put that together, hopefully. Let's read number 5. So a rectangular ball field is 120 yards long and has area of 10,200 square yards. What is it with? So what are they asking? What are they giving you? They give you a length and they give you an area. And we're talking about a rectangular field. And so we want something with area of a rectangle. So area is length times width. And so the first thing, if I'm filling in my variables here, my A is my area. That is the 10,200. And this is equal to my length times my width. So they give me my length is 120. And I still need to find my width. So if I don't know my width, let that be the variable. And now this is 120 times W equals 10,200. This is similar to everything else we've had, right? If it's being multiplied by 120, we have to divide both sides by 120. So I believe in this one, W should give you 85. And here I've talked about it. When we go to area, we talk about square yards. When we talk about length and width, we're talking about the single unit yards. So coming back and putting those units on things is kind of important. Okay. Just a few more. 6. So one angle of a triangle is 10 degrees more than the smallest angle. The largest angle is 5 degrees more than 3 times the smallest angle. Find all 3 angles. Okay. So what are we looking for? How many variables should we have, I guess, is the first question, right? And I think it's right here. It says find all 3 angles. So there are going to be 3 angles. So you can do X, Y, Z, A, B, C, D, E, F, anything you want. You got to find 3 letters. So I think I did A, B, C. And A is going to be the first angle. B is going to be the second angle. And C is going to be, wait for it, the third angle. Okay. I have 3 angles. I have a first one, second one, and third one. Okay. So now let's go back, read this statement. One angle of a triangle is 10 degrees more than the smallest angle. So I haven't really defined which one's the smallest, which one's the largest. But I think if I start doing that now, so one angle, let's do the first angle, is 10 degrees more than the smallest angle. So we want to say this is 10 degrees more than the second angle. Sounds like a good one. So in order to do that, I want to take my second angle and I want to add 10 to it so that when I have my second angle add 10, my A will be 10 degrees more. And I just did this. I've kind of implied something when I made that statement, right? I am implying that this is now my smallest angle. So that might be a good thing to go back and note that now that we have just made that our smallest angle. Okay. Now we got another sentence. The largest angle is 5 more than 3 times the smallest angle. So now we're using the largest angle. So A is not my largest angle. B is my smallest angle. It's definitely not my largest. So C is the only one I haven't used. So I think I'm going to have to make this my largest. I think I made that by default now. And so they say the largest angle, or C, is 5 more than 3 times the smallest angle. So 5 more means that we're going to end up adding 5. 3 times the smallest angle would be 3 times B. Okay. So we have these two statements from what they have told us in English there, right? There's one other thing that we need to take from this, and they say these are angles of a triangle. And so we know something about the angle of a triangle. The angle of a triangle, A, B, and C, if we add them all together, the interior angles of a triangle are going to sum up to 180. We have these three equations that we can pull from the English in that problem. Okay. So I think the approach that you probably want to do is start out with this formula. And if we start out with this formula, we can make some plugins. And so this A, instead of A, I can type in B plus 10. And so instead of A, I'm going to do B plus 10. I still have to plus B. Instead of C, I can do 3B plus 5. And so instead of C, I'm going to write out 3B plus 5, and this is equal to 180. So first angle plus second angle plus third angle is what I'm still doing. Just writing it a little different way. Making my substitutions that I can make. And now you might notice, if I do that, this gives me nothing but B's and constants. So now I can solve for B. I need to do a little bit of cleaning. This is 1 plus 1 plus 3 should give me, what, 5B on this side? And I have 10 and 5, that should give me plus 15. And this is equal to 180. Okay. So I'm still doing a little bit of solving. 5B plus 15 equals 180. So in order to solve for B, I need to subtract 15 from both sides. This is going to give me 5B is, what, 165. And then the next step is I divide both sides by 5. So if I'm dividing by 5, B is going to give me 33. And now it seems like we're almost there. We got this B equals 33. And now I'm going to ask you, is that my solution? And if you said yes, you're 1/3 of the way there, right? You're 1/3 way correct. That is part of your solution. We still have to find two other things. Okay. What do we have to find? We have to find the other two angles. So we have found the second. This should be the smallest angle if we figured things out correctly. So how do we find A? Well, A's got this nice B plus 10 thing we can plug into. So if A is B plus 10, then A is going to be what? 33 plus 10 is going to be 43 degrees. The other one, C, we had this nice little formula, 3b plus 5. So 3b plus 5, we're doing 3 times what? 33? That's it. Plus 5. Ooh, sorry. 3 times 33 plus 5, I believe that's what? 99 plus 5? That should give me what? 104, I believe. Okay, so we found angle A, we found angle B, we found angle C. Okay, what if I want to check this? What's one easy way to check this to make sure I have it correct? These are four angles of a triangle. Guess what I can do? I can add them together and I can see if they equal that 180 like I said they did, right? And so we can check it by plugging it into that other formula. The A plus B plus C equals 180. And it checks. So it should be correct, hopefully. Okay. Getting close. Solve the formula for the area of a triangle for the height h. So back to the area of a triangle. We've used it a few times. We're going to use it once more, I think. Area is base times height. And we want to solve it for h. I was in that club one time. Okay, so we want to solve this thing for h. This is a half base times height. There's a few ways you can do this. If we want to get rid of a half, we can divide by a half, that's okay. The other way is we can multiply by the reciprocal. So if we multiply by the reciprocal, multiplying by the reciprocal, let me do it maybe. Would be 2 over 1, or multiplying by 2. If you want to get rid of a half, you multiply by 2. So now I put it over 1. I'm already going to drop it with the next step. So this is on that side. This thing and this thing should simplify out. This is b times h now. Okay. Let me try to clear this up just a little bit with this autofocus. Hold on, here we go. There we go, that's a little better. A little less blurry. Okay, so 2a equals b times h. So we want to solve for, we're still solving for h. So what is happening to h? It's being multiplied by b. So the next thing we need to do, divide both sides by b. If we divide both sides by b, this side is just h now. I'm going to maybe swap sides. This side is 2a over b. Oh man, and after all of those things we've been doing, it really feels like you maybe want to do something more to this, right? But guess what? We got 1h to the first power. We have solved for h. That's all we need to do. That's it. I'm trying to think. Maybe one thing that might go wrong is if you do this correctly, you might end up with not. End up with like a half on the bottom. So typically, if you did this and you ended up with something like this, typically we don't write fractions and fractions. We try to clean those things up. So what would you do? Multiply both the top and bottom by 2, and when you do that, it should get you to that step. So multiplying by 1 does not change the number, right? And this is just multiplying by a big fancy 1. Oh, I might have lied to you on using this. We're going to use the area of a triangle once more for this last problem, I believe. A triangular flag that is 12 feet at the base uses 180 square feet of fabric. What is the height of the flag? Oh, okay. Are we using area? Huh. What's the indicator there? Okay, so triangle flag, it's 12 feet at its base, 180 square feet. So the indicator here really to me that we're using area is this thing right here. They're saying square feet. And if we're talking about square feet, we're talking about a measurement in 2 dimensions. We're talking about area. And so we'll use measurements in 2 areas or square feet to talk about area. We'll use what, cubic feet to talk about volume, right? But that's when we get to 3D objects. We're still in the 2D here. So let's talk about this one. We know we're going to have to use what? Area equals 1/2 base height. So let's do it that way. There's actually, I think there might be a few different ways you can do this one, huh? Let's think about it. So area equals 1/2. But if you do work, use the work you did, right? It might come in handy. Let's see. This is also a formula relating to triangles that we just solved. So let's look at this. A rectangular flag is 12 feet at its base, so we can fill in 12 to the base. So 1/2, my base is 12. I don't know what my height is, but they give me the area is 180. And so I know I'm using just a second. I know I'm using this formula or this formula. They are the same formula, just rearranged, right? So that is one way I can do it. And this is perfectly fine, and it's probably not going to take you very long. 1/2 of 12 is 6. Then we're dividing this by, what, 6 to get my height is 30, right? So that may not take you very long. But let's look at this one. My height is 2 times my area is 2 times 1. And we're going to divide that by the base, which is 12. So I'm doing what, 360 over 12? I believe that is still going to give me 30. And so while they are the same formula, this one might be a little more direct when we're solving for height. We had to do a little bit of solving. We had to do some division here to find h. Here it was already solved for h. We just plug things in when we crunch the numbers, right? Okay. So sometimes if you use the work you did in the previous problem, it might save you a little bit of time and headache and heartache in the long run, right? Okay, so I believe that's the last problem. Thank you for sticking around, and I will see you in class Monday.